So thanks for inviting me. It's a pleasure to be here. There aren't really any real singularities in this talk, so I'm sorry. So I'm going to talk about the Pila-Wilkie theorem, which is about counting rational points on sets definable in O-minimal structures. So I'll start by just talking about definability briefly. So I'll give a quick description of definability. And the Pila-Wilkie theorem. Let's start with F. Let F be a collection of functions taking Rn to R for various n. And we start with this. These are the basic functions. And then we form a larger collection, F tilde, which contains, it's the smallest collection of functions containing all of these functions and containing all polynomials and closed under composition. So I just mean if I have a bunch of functions in here and I use them to form the coordinate functions of a map and I compose with another function, I want that the composition to be in here too. And then we form a collection of subsets of Rn for various n by doing the following. We start with all sets of the form x in Rn such that f of x is 0, or x in Rn such that f of x is positive, where I've got some f in this f tilde, which is defined on Rn. So these are analogues of semi-algebraic sets, and then take close under union intersection complement and products, Cartesian products. And then I do the analog of sub-analytic, so I project, so close under coordinate projections. And then we iterate steps 2 and 3 forever, and we generate larger and larger collection of sets. So this isn't really the way to think about definability, but it's useful if you've never seen it. So the collection we get, those sets are called F definable. call the resulting collection of sets F definable, and call the subcollection where we stop here at step 3 and don't iterate, we'll call them existentially F definable. So the sets obtained by 1, 2, and 3, but never iterating. So we just do, I mean, we can take arbitrary numbers of projections, but we call, I mean, this is, sorry, horrible notation, but you'll probably never see it outside of this talk. We call them existentially F definable. So for instance, if I take my original F to be the empty set, I get semi-algebraic sets, because I then add all polynomials and do this. And if I take, so the empty set definable corresponds to semi-algebraic. If I take little an to be the collection of all analytic functions on compact boxes, which I then just extend by 0, so I call these all restricted analytic functions. Well then the an definable sets are very closely related to subanalytic sets, to globally subanalytic sets. So an definable is approximately globally subanalytic. If you take the sine function and you do this, you get all projective subsets of reals, and then you kind of run into set theoretic questions about, I mean, I guess it's independent of ZFC whether they're all measurable or something. Is that right? So it's, I mean, there's a huge, because you can put anything for F, right? So as soon as you put something like sine, you'll get very non-tame behavior, but will be at the tame end. Okay. Now, most of the talk will take place in the setting of my F will be an, so these restricted analytic functions together with the unrestricted exponential function. I'll go a bit beyond this at times, but this is kind of definable in here is a good example of an O-minimal structure. So I'll just call this definable for now, for the Pila-Wilkie theorem at least. Okay, so the Pila-Wilkie theorem is about rational points. So that just means you have a set like this, and you look at the points with rational coordinates. And you want to try and count them, and there might be infinitely many. So we introduce a height, and we count up to height. So for a rational, Q equal to A over B in lowest terms, let height of Q be the maximum of the absolute values of the integers. And then if I have a tuple, I just take maximum of the heights of the coordinates. So for Q and Q to the n, take height of Q to be the max of the heights of the Qi, And then if I have my set, x in Rn, and I have some h, we'll put xh to be the set of rational points on x of height at most h. So what we want to do is bound the size of this for certain x. I mean, in fact, a huge amount of number theory is concerned with sets like this for various x, right? But we'll be interested in kind of transcendental x, as opposed to perhaps the more usual algebraic x. But just for instance, if I take x to be q, and I look at the points of height h, this is about c to the h squared, c times h squared, because if you think I have about, this is q. I have about 8 choices for A and about 8 choices for B. Okay.
So what is Q of H again?
So Q, yeah, sorry, this is horrible notation. So this is, it's the points in Q of height at most H. So it's just all rationals of height at most H, so I have about 8 choices for the numerator and about 8 choices for the denominator.
Could you write down the definition?
Sorry?
Could you write down the definition?
It's here.
Where is Q of it?
Q, here, X is Q.
Q is X. Q is X.
Yeah.
Q is X normal.
So this was just meant to show that the following theorem is non-trivial. Okay, so the theorem, well, so this is a special case of the Pila-Wilkie theorem, but it's kind of representative. So suppose x is definable, so which means definable from restricted analytic functions in the exponential function. And suppose x contains no infinite semi-algebraic set. Then, for all epsilon, there is a C such that for all H, this set has at most C H to the epsilon points of height H lying on it. Okay, so we have a definable set, and let's just assume it contains no infinite semi-algebraic sets. In that case, we can get this kind of bound. So this is definitely non-trivial, right? Because there's more points that could be there. And it would fail if X contained a line, say, a rational line. Okay. So, I mean, there are lots of ways that this can be improved. You can weaken this assumption a great deal, and you can count other points as well. But I'm going to focus on two possible ways of improving it. So the first...
Excuse me, the C, how big is C?
Well, that's number 2. So one is, can we replace this with something that grows slower? So can we improve the bound to, say, C log h to the k for some c and k, to, can we compute c in terms of epsilon and x if we're given some kind of concrete x? Well, so how effective is c? I mean, 2 doesn't make a lot of sense in general, but for concrete sets it makes sense. So 1 is impossible in general, so we can't do 1. In general. So there are analytic curves, restricted analytic curves, for which this bound can't really be improved. But they're kind of artificial, so we might hope for natural analytic curves you can improve this. And the motivation for 2, so this theorem has been applied to quite a lot recently in Diophantine geometry to get finiteness results. So we'll see some examples later on. And in some of those results, the only obstruction, or the main obstruction to effectivity for the finite sets involved is the application of this theorem. So the motivation for 2 is, in kind of quite concrete situations, we want to be able to work out the constants so that we get effective finiteness results in Diophantine problems. Okay, so I'll give some instances where we can do these kind of things. So I'll give 2. The first one is a bit strange, but it's kind of, well, it's useful. Oh gosh. So this is that one. Okay. So I won't really say very much about proofs. I'll say a little bit about proofs after I stated the theorems, and then I'll give some applications. So there have been various results. I'm just going to give a couple. So this is due to Gareth Boxall and me. Okay, so suppose f. I should say. I mean, I'm only going to talk about curves really now. So x is going to be the graph of a function. So suppose f is complex analytic on, say, the disk of radius 2 around the origin. And suppose f of 0 is q times pi to the k, where q is a non-zero rational and k is an integer, a non-zero integer. So this is quite an odd assumption, but let's take x to be the graph of f restricted to 0, 1. So this is a restricted analytic function, right? So Pila-Wilkie applies to this, and in fact, in this case, for one variable analytic functions, it goes back to Bombieri Pila. It's quite a lot older. But under this assumption, so then there is a C such that for all h at least E, on this set, the graph of f over the smaller interval there are at most c times log h to the 4 points. So without this assumption, this is false, because you have analytic curves for which the h to the epsilon bound can't be improved. And with this funny-looking assumption, you get quite a substantial improvement. In fact, you get down to, it's like c log h cubed log h or something. But I don't need to be too precise. And here c can be computed fairly easily if you're given q, k, and a bound for the maximum of f on this disk. C can be computed from max the max of f on the big disk and q and k. So yeah, okay. So this is a funny assumption, but there are lots of examples which it applies to, and there is some flexibility here. You can put other numbers, some other numbers. Okay, so there's certainly flexibility. We can work on a disk that's not centered at 0. We can center a disk at a different rational point, and it doesn't change the result. And we can work on disks of other radiuses. So let's take f1 of z to be zeta of z, so Riemann zeta times z minus 1. So this is entire. Then, well, if I put 2 in, I get zeta of 2. F1 of 2 is pi squared over 6. So I can work around point with point z equals 2, and I can apply this result. So in this, for this example, in fact, Massa has done better. He has a c log h squared bound, but his techniques are quite specific to zeta. So another example is, well, I can take f2 to be zeta of z times z minus 1 over pi to the z, so that positive even integers, I get rationals. Now minus 1, this is pi over 6, yeah. So I can apply the theorem, working on a disk around minus 1.
So is it essential that f is not semi-algebraic?
Well, in fact, that's coded in here, really. I mean,
only this counts.
Yeah, you see.
No, k. Oh, k is not there.
Yeah, k's. Yeah, this is all you need for this. It's slightly surprising that you don't need actually transcendental. Right, but you're putting it in here.
So these only algebraic to real coefficients.
But they sort of have to be real, not algebraic, or not rational. And another example that doesn't quite fit in, but you could make it fit, is if I take gamma of z, I have gamma of a half is root pi, which, it's not an integer power of pi, but it's almost. So you can get a result for gamma too. And in this case, Besson has adapted Masser's argument to get a similar bound to this. So for kind of, if you really work with more properties of the function, you should be able to do better. So this is quite a crude property of the function, but you apply it applies to lots of different functions. So okay, so that's not at all connected with real singularities. The next one is a bit more. So, definition. A sequence f1 up to fl of analytic functions on an open set in Rn. So these are real analytic now. Is a Pfaffian chain if there exist polynomials Pij in n plus I variables such that dfi by dxj is Pij of x, f1 of x, up to fi of x. So is that visible? Yeah. So I have a sequence of functions, and as I go along, the derivatives can depend on the functions before and the function itself, not on the functions in the future. Okay, so I'll give some examples of Pfaffian functions later on, maybe, but the exponential is Pfaffian. Sine restricted to an interval is Pfaffian, and there are various other examples. So if I have time, I'll give some in a bit. But, we'll write Pfaff. Let Pfaff be the collection of all Pfaffian functions on Rn for various n. Okay, and then the theorem. So this is well, it combines work of Pila and work of Margaret Thomas and me. So here, suppose X is a transcendental analytic curve connected which is existentially Pfaff definable. So I can get it by starting with Pfaffian functions, closing under unions and so on, and projecting. Then there exist C and K such that for all H, at least E, X has at most C log H to the K rational points of height H. So we get a similar kind of bound. These are less explicit now, but you can compute them. If you're given an existential definition of f from Pfaffian functions in a certain form, you can compute them. I mean, essentially these things here will depend on the complexity of the differential equations of the functions involved. Okay. So I'll just say a very small bit about the proofs. So you prove these kind of results in two steps, really. You've got your set, and you want to count the points of height h. So first of all, you show that the points you're trying to count, the rational points of height h, lying on your curve, also lie on some algebraic curve of degree roughly log h. So you construct a polynomial in two variables, say, such that q f of q is in your set exactly if p of q f of q is 0. So step one is find a polynomial p such that so let's say x is the graph of f such that q f of q is in your set of points if this then p of q f of q equals 0. And you find p with degree around log h. And then you count the zeros of p of x, f of x. And you see here, you can, in the Pfaffian case, you can use Hovansky theory to do step 2. And in fact, you use it in step 1 too. In the complex case, you kind of, well, you find more conditions. That P satisfies further conditions, and then you can reduce. You can use complex analysis to to reduce this to lower bounds on, say, P of 0, F of 0, and then, well, you find that P can have integer coefficients, and then P of 0, F of 0 is an integer polynomial in pi, so it's not 0, and then you can use an explicit lower bound for such a thing. Okay, so that's just a sketch of the proof. I mean, this is in most cases, this is the hard step.
Where you can find this P, polynomial P?
Well, you find it, I use a paper by Massa to find it. But it's, you have to construct it. I mean, so, well, there's two methods. You can use Siegel's lemma from transcendence theory, or you can use something called the determinant method, which was introduced by Bombieri and Pila. I mean, are you going to do?
I'm not going to do that.
Oh, okay.
but the bound for the degree, because this is my, I believe, the difficult part also. Why you can find the polynomial of this degree bounded by not for this problem, for this.
Only the points of height h. Yeah.
Yeah. I mean, I can show you, but perhaps not now. Okay.
Well, say something very quick. Take the generic polynomial of degree log h, which has about log h squared coefficients, and you can find integers that make it 0, with a certain number of pairs of rationals. Well, that's just a question of solving linear equations. And you arrange that you have many more variables and equations.
And then we use some estimates of the number of roots, right?
Yeah, this.
What sort of estimates?
Well, they vary according to what case you're in. So in this case, I use Havansky theory.
What?
Havansky.
Okay. This is what I suppose.
Well, you have to work a bit because, so if x is the graph of a Pfaffian function, you could use Havansky straight away. Once you've done this, which is not so trivial in this case, if it's a projection of things defined using Pfaffian functions, you have to work a bit to get to be able to use.
There are slightly more modern estimates than I mean, there are Gabriel Vorobyov and Benjamin.
So Gabriel and Vorobyov don't really do more. Well, yeah. I mean, we need results of Gabriel and Vorobyov when we look at surfaces, actually, more than curves. For curves, we can just use Havansky. For surfaces, we have to do kind of effective stratification procedures and so on. But that's I just wanted to talk about curves. I don't know about Bignamini. I know who he is. I mean, I know him. I don't know what he's done recently. I mean, he's a busy guy, right? Okay, so I've got 10 minutes left. So I'll just give some applications now. So these might look completely off the wall. So most of the applications of Pila-Wilkie are instances of things called the Zilberpink conjectures, and there's been a lot of work on these things. I'm not sure there is a fixed Zilberpink conjecture. I'm not sure people agree on quite what it should be. That won't concern us. We'll work with this family E lambda of elliptic curves. So it's the Legendre family. Lambda is a complex number, different from 0 or 1. So I have an elliptic curve, and I say that its two torsion points are the origin 0, the point with x coordinate 0, point with x coordinate 1, point with x coordinate lambda. And then, okay. So the theorem, so this is a very special case of something due to Bertrand, Bertrand and Massa, Pila, and Zanier. So they prove a much more general result than this, but it implies that there are at most finitely many, so there might be none, roots of unity lambda such that the point P lambda, which is given by, has x coordinate 2 and y coordinate either of the square roots of 2 times 2 minus lambda, is torsion on E lambda. Okay, so we have this curve. So we know that the points with x coordinate 0, 1 and lambda are torsion. So we look at the point with x coordinate 2, and we look at roots of unity such that that fixed point is torsion. And the theorem says there's at most finitely many. If you leave off the roots of unity, there are infinitely many. So this theorem, so this is part of a general result which tells you if you have a curve in gm times E lambda that's not of a certain form, you have finitely many torsion points. So these lambda, a root of unity such that P lambda is torsion, is a torsion point on the group gm times E lambda. And these results are about torsion points on curves. In fact, their result is about, it does the general case of an extension of E lambda by a multiplicative group. Okay, so their theorem gives this finiteness result, and it gives no way, even in principle, to compute this finite set. So it gives no bound on the degree of the root of unity. So theorem due to Habegger, me and Massa. So this uses the ideas of the proof of my result with Boxwell about where you have a value pi. You can compute, there's a bound on the degree here. The previous result is effective. So that's nice. Unfortunately, this completely fails if, say, you change 2 to -1. So it's not very robust. A slightly better method comes using Pfaffian functions. So just, well, so I'll have to state the theorem. It will look a bit funny. So this is due, well, okay. So I haven't checked every detail of this. This is a claim, This is due to me and Harry Schmidt. So if I fix alpha, a non-real algebraic number, so there is an effective C such that if lambda is a totally real algebraic number, such that well, the point with x coordinate alpha and whatever the y coordinate is torsion on E lambda if that, then the degree of lambda and the height of lambda is at most c. So this says there's this if we look at totally real lambdas such that some non-real point is torsion, we can compute all the lambdas. There's only finitely many, and there's an effective way of computing them. So this uses Pfaffian functions, uses a result of Legal, Sands, and Speisiger to show that certain functions are Pfaffian, which is nice. And very recently, I don't want to write this down. I mean, this is, I think this is okay. Very recently, we've extended this Pfaffian method to the circle, so we can put any number here. But yeah, that's for another day, perhaps. Okay.